Hello, this is the second video of the series Description of Motion. In this video, we will learn about velocity vectors. Continuing from last time, we will consider a situation where an object is in motion. Suppose that the object changes its position along this path. Also, suppose that the object's position at time t1 is here, and its position at time t2 is here. Let's consider the amount of change in the position vector between time t1 and t2. The amount of change is rt2 minus rt1. This difference in the position vector is called the displacement vector. This displacement vector corresponds to this red arrow in the figure and represents how much the object's position changed between time t1 and t2. Now we can consider several quantities using the displacement vector we have just defined. First, we consider the absolute value of the displacement vector, that is, the magnitude of the vector which gives us the distance between these 2 points. Focusing on the amount of change in the position vector when there is a change in time from t1 to t2, we find that the time taken here is t2 minus t1. Therefore, this distance divided by the time gives the speed. This is called the average speed between t1 and t2. We can further consider the quantity obtained from dividing the displacement vector by the time it took to change it. This is called the average velocity between t1 and t2. The numerator is the amount of change in the position vector, and the denominator is the time it took to change it. So this quantity gives the amount of change in the position vector per unit of time. Now we have considered the change between times t1 and t2. However, we can choose t1 and t2 in any way we like. Note that the displacement vector we are considering is determined only by the position of the object at time t2 and at time t1. Therefore, these quantities defined from the displacement vectors do not include the precise information about the motion of the object between time t1 and t2. Therefore, the closer the time t2 is to t1, the more accurately the displacement vectors and quantities can represent the motion. Now, in order to accurately describe the motion around time t1, we consider a small time interval delta t and focus on the motion between t1 and t1 plus delta t. We are interested in the position after a small delta t from the position at time t1, that is, at time t1 plus delta t. The displacement vector created from these two position vectors is written as delta rt1. This displacement vector corresponds to this arrow here. We can now consider taking this delta t smaller and smaller. Then this object gets closer and closer to the position of the object at time t1, and the displacement vector gets shorter and shorter. Therefore, to define the instantaneous velocity vector at time t1, we divide the displacement vector defined in this way by the time delta t taken for its change, and take the limit as delta t approaches 0. And if you consider its magnitude, we can define the instantaneous speed at time t1. Now the velocity and speed we have just defined are at time t1. However, this discussion is valid for any time t. So we can define them in a more general way by replacing t1 by t, and we get this final expression here for the definition of the velocity vector. Note that velocity is defined as the displacement vector divided by time. And since the displacement vector is a vector, the velocity is also a vector quantity. The direction of the velocity vector generally corresponds to the tangent direction with respect to the path drawn by the motion of the object. This can be easily understood by considering the displacement vector. Just as done before, let's suppose now that the position of the object at time t is here, and its position at time t plus delta t is here. The displacement vector of the object at this time interval of delta t looks like this, and as this delta t gets smaller, the direction of the displacement vector gets closer to the tangent direction of the path of the object's motion at this point. The magnitude of the velocity vector corresponds to the instantaneous speed at that time. So it is good to notice that the velocity vector is defined using the displacement vector. We saw that the position vector could be represented using its components. The same is true for the velocity vector. Since it is a vector, it can be expressed in terms of its components under appropriate coordinates. Now let me explain a few things to keep in mind about velocity vectors. First of all, delta t, which was considered when introducing velocity vectors, was called a small time interval, and quantities with delta written like this are sometimes used in physics. The standard definition of the delta quantity is that it is a small quantity. The exact definition of the velocity vector is given by taking the limit as delta t approaches 0, but sometimes it is enough to make an approximation. If one takes a delta t small enough, these two quantities are approximately equivalent. So to an approximation, we can also write the velocity in this way. Second, the standard unit for velocity is meter per second. This is displacement vector divided by time, where displacement vector is a measure of length such that its absolute value gives the distance. Therefore, since the standard unit for length is meter and for time is second, the standard unit for velocity is meter per second. We often think of motion with constant velocity, but motion with constant velocity means that the tangent direction to the trajectory is constant. First of all, since velocity is a vector, it has a direction and a magnitude. So if the velocity is constant, it means that the direction of the velocity is constant, which is the direction tangent to the trajectory. The magnitude of the vector is also unchanged. What is possible for such motion is a motion on a straight line with a constant velocity. Such motion is called uniform linear motion. The magnitude of the velocity is the speed. We will call a motion with constant speed a uniform motion. Constant speed does not necessarily mean that the velocity is constant. It is possible to have a constant speed and at the same time have a varying velocity. In other words, there are uniform motions that are not uniform linear motions. A typical example is a uniform circular motion. When an object is moving around a circle at a constant speed, the speed of the object's motion is constant, but the direction of the velocity is tangent to the trajectory, which changes with time. Therefore, the velocity vector is not constant. It is important to be able to distinguish well between velocity and speed. Velocity, as I have explained, is closely related to the concept of differentiation. The component of the velocity vector can be thought of as a derivative of the components of the position vector at time t. I will now explain about this a little bit more. First, we consider the change of the position vector between time t and t plus delta t, and define the velocity vector in this way. Let us consider an x-axis and y-axis in suitable orientations. If this is a two-dimensional motion on a plane, then the position vector could be expressed in two coordinates, xt and yt. Let us denote the magnitude of the velocity vector in the direction of this x and y-axis as its component vx and vy. Then, from the definition of the velocity vector, we can write vxt and vyt in this way. For vxt, it is the x component of the position vector at time t plus delta t minus the value at time t divided by delta t. This is exactly the definition of a derivative that we learn in mathematics. In mathematics, it is often explained using fx, which is a function of x. The derivative f prime x is the limit of f at x plus delta x minus f at x divided by delta x as delta x approaches 0. Sometimes this is written as df dx. In this case, We consider the average change in x, a function of time t, from t plus delta t to t, and we take the limit as delta t approaches 0. This can be written as dx dt, the derivative of x with respect to time t. The same is true for the y component of the velocity vector, dy dt. From the definition of the velocity vector, we see that its components turn out to be derivatives of ordinary functions. So the velocity vector can also be written as the derivative of the position vector with respect to time. Finally, I would like to look at one specific example. This is an example of uniform linear motion. The definition of velocity is written here. In this example, the position vector is the same as the one we considered in the previous video, and is expressed as follows. Time t is p seconds. P can take values such as 0, 1, 2, 3, and the position vector has an x component of 2p meters and a y component of 3p plus 1 meter. When considering a velocity vector, we consider a small time interval. So let us define delta t as a small change delta p times seconds. Then, according to this definition, let's look first at the x component of the velocity vector. And as I mentioned earlier, let's consider the amount of change from the value of the x-coordinate at t plus delta t to xt and divide it by delta t. Now, if we substitute t plus delta t for the part that corresponds to xt, we see that 2p becomes 2p plus delta p. Then, subtract the x-coordinate 2p at time t and divide it by the change in time delta t, which is delta p seconds. If we calculate the numerator, we see that 2p cancels out, and the delta p that is left is cancelled by the delta p from the denominator. So we are left with 2 meters per second. A similar calculation for the y-coordinate gives us 3 meters per second. This is a constant vector with constant magnitude and a rotation independent of time t. In other words, the velocity is constant, it doesn't change. This represents a uniform linear motion. The object is moving this direction, and at every point it has the same velocity with the same magnitude and the same orientation. In this video, we learned about velocity vectors. To define velocity vectors, we first looked at displacement vectors, and from there we looked at things like average speed and average velocity. After looking at the definition of velocity vectors, we also discussed the relationship between velocity and derivatives, uniform motion and uniform linear motion. So this is the end of this video. Thank you for watching and see you in the next one.